Okay. Okay. Hi everyone. So let's start. I don't know what number lecture is this. Is it 11? Okay. So this is lecture 11. That's good. That's great to know. Okay. So last thing we did, you remember, was tangent vector to a curve, right? So last thing we did was tangent vector, and then immediately we discussed the idea of velocity and the idea of tangent line also, as just building on this first idea. And this immediately gave us tangent line, and then we did some question about tangent line. Maybe I should emphasize again the difference between velocity and speed, right? So now we can just see the difference between velocity versus speed. Okay, so yeah, this is a good place to discuss that. So here it comes. So velocity, so what was the setting? So we had a curve, right? A particle moving in space, like r of t. I mean, t belongs to some interval, dA, right? So this r is a function from this interval AB to R3. So you can imagine this gives us equation of motion, or it's really the path of the particle. It's more than path, right? It also tells you how fast it's moving. It's not just about the curve, it also tells you how fast it's moving. Anyhow, so then velocity we defined last time by definition that it's r prime of t. So it's a vector, right? Of course, it also depends on time t. It changes from time to time, right? So it's velocity at time t. So you know that right now we are interpreting the real line as the time axis. But in some other contexts, you can interpret it as position axis or other things. But here we are interpreting as time axis. That's what we're doing, right? Okay, so this is velocity, which is a vector. But what's speed? Now, speed is the following thing, right? You know that, I'm sure you have seen it. Speed is length of this vector, is norm of this vector, right? This is norm, this is r prime of t, right? So that's speed. So it's a scalar, right? Is a scalar. So this one, velocity, while velocity is a vector, speed is a scalar. It's just a number. And in fact, it's never negative the way it's defined. It's 0 or above, but this guy, we cannot even say it's negative because it's just a vector. It just goes this direction, that direction. So that's one kind of a bit of nuance about the difference between velocity and speed. You already know it, I just emphasized. Tangent line, we did tangent vector. So now for today, there is a concept that it's good to know. That's the concept of unit tangent vector. Right, so it's a unit tangent. So today, we look at the idea of unit tangent vector. So so the way it's defined, it's t. It's again a vector, but what we do, we just take the derivative of this guy. We just take the velocity and divide by its speed, divide by its length. Right? So we just take r prime of t divided by norm of r prime of t, length or magnitude of R prime of t, right? So you notice that this has one feature. What is the most pronounced feature of this vector t, the way it's defined? Yes, I mean, that's actually the way we define it. It's a unit tangent vector. It's unit length, right? So even from the name, it's kind of suggested that it should have this property. So note that it's length is equal to 1 for all t actually. Right? So it's always a vector that has length 1. And we made it like that. We forced it to be like that. We divide it. So if this is the velocity, for example, r prime of t, we just divide it by its length. Of course, we can do this when r prime of t is different from 0. If r prime of t is 0, we cannot do it. We cannot divide by 0. Right? So also note that we need, for this to make sense, we need r prime of t is equal to 0. You cannot talk about unit tangent vector to a particle that's moving in space, and at the moment where the velocity is 0, it doesn't have unit tangent vector, which disappears.
So should that be doesn't equal 0?
So, sorry?
We need r prime t not equal 0?
Thank you. Yeah, exactly. Right. So we need this condition, and then after that, everything is okay. We can just do it. So let me give you an example. Very good. Find the unit tangent vector to the curve. So r of t equal to, so let me just give you a simple example, cosine of t, negative sine of t, and 2t at time t equal to pi over 6. It's a strange way of measuring time, but so you don't have even to say this is a time. You can just say this is just at time. At point t equal to pi over 6, right? So you don't even have to say this. That's it. So, I mean, the solution is clear what you have to do. So let me just quickly do it. So solution. Okay, well, we have to take r prime, right? There is a question, it seems, in the chat. Not much. Profs explain difference between the speed and velocity. Oh, okay. So yeah, okay, very good. That's right. That's what I did indeed. So solution. Well, what is r prime of t? So r prime of t, we have to take derivative of this, that, and that, right? Just component-wise change derivatives. This is equal to negative sine t, and then negative cos t, and then 2. So what is r prime at the point pi over 6? That's negative sine of pi over 6. Yes, negative cosine of pi over 6. And 2. So let's, what is sine of pi over 6?
1/2.
It's 1/2, yes. This I recommend you to memorize, to know. It's advisable to know that as well. I mean, in general, you know, sometime in the street, someone may be offering you money by asking you what is sine of pi over 6. So minus 1/2. And then what is minus cosine of pi over 6? Yeah, cosine of power 6 is root 3 over 2. That's right, but there is minus, so minus root 3 over 2. And this guy is 2. It's root 3 over 2. You get square it, you get quarter, and 3 over 4. Yeah, they add up to 1, and this is correct. All right, so now we have to divide this vector by its length. So what is the length of R prime of power 6? Okay, so that's the square root of quarter plus 3 over 4 plus 4 square root of, well, this is 4, 1 plus 3, 4 times 4 is 16. 4, 16 is 20, so a square root of 20 over 2. So this is a square root of 5, actually. Okay, so then R prime, so then T at pi over 6, which is indeed R prime of T divided by norm of R prime of T. That's equal to 1 over root 5 times the original vector, which is minus half. So let me erase this. Minus half minus root 3 over 2 and 2. And you really don't have to simplify. I mean, it's just, there's no point of simplifying this. It's already clear. Any questions about this issue of unit? In fact, you may wonder why we go through this practice of finding unit tangent vector, because it looks like something unnecessary torture to do that. But you will see soon that it has amazing kind of use. Very soon you will see its use. It's extremely useful idea. So once we discuss arc length, it will come to fore and will prove itself to be worthy of attention. Okay, so that's that. Now let's go to next section, which is about arc length, which is closely related to this idea, as I said. So arc length. I'm going to erase arc length. I don't think it's one word. I mean, no, it's not one word. We have archangel, but we don't have arc length. Is it one word?
I think so.
Yeah.
Really? It can be two words though, but yeah, there's a arc can be used as a prefix. That's right. So of course, like archangel, arc.
No, it's yours.
Oh.
Yeah.
Yeah, you're right.
Yeah. Well, yeah. I mean, like my arch enemy or nemesis. Archangel, Arctic. Well, Arctic is one word. Okay. So yeah, okay. So well, anyhow, this may be one word or two words. As I say, it's two words, so but that's okay. Arc length of a curve. Okay. So now the idea is this: we have this curve R. So now we are thinking of it as a curve going from some interval AB to R3. Again, the idea is always the mental image that we should have of this function is that we have this curve going from point A, being R of A in space to R of B in space, right? We have this thing. And now we want to measure somehow this length, right? Of course, I mean, if it is a straight line, really a straight line between these 2 points, you know how to measure it. We already did it in earlier sections, right? We know how to measure the length of this straight line from vector R of A to R of B, but this is more complicated. The first thing to do is to define it first, right? We have to define it. And then we have to have a way of computing. Okay, so first define the arc length. Define the arc length. And then we will derive a formula for that. But it's very important to know what is the definition, because I mean, we have to define it somehow. It's not obvious what the concept means. I mean, intuitively it's clear, because if you go and do experiment, you know, have kind of rope kind of laid around this curve, and then you can open the rope without stretching or contracting, and then you can just put it on the line, and then you can measure. So this is kind of intuitively clear what the idea is, but still we need mathematical definition. So the idea now is that we divide this interval into small pieces. This is, as usual, AB into small subintervals. So these subintervals, I mean, you can even take to be of same length. So maybe you divide into n pieces of subintervals. You go from here to there, from there. And then you find the corresponding images on the curve here. So this is that. And then we approximate the curve by straight lines. So we connect by a straight line. So here you will get a kind of polygon approximation of this curve, right? Get polygon approximation. Am I in the line? Seems so, yes. We get a polygon approximation to the curve, to our curve. And then what we can do, we can just take, so now we are back to the case that we have just a bunch of straight lines. So we add the lengths of these straight lines, and we hope for the best. Namely, we hope that as we take finer and finer subdivisions of the interval, eventually these numbers will converge to some number, and that would be the length. And hope for the best. And hope for the best. So I don't write anymore what do we mean by hope for the best. I just said what we mean. In the sense that you take these numbers and you take finer and finer partitions here. And we hope that these numbers, as you add them, will converge to a number, and that number would be our candidate for the diffusion. And this sort of approach stands to reason, right? Because it just says that, okay, we are approximating by these straight lines, and these straight lines, in some sense, is approaching to this curvy line, and then the length might be actually, yeah, this is indeed what people did from antiquity, from a long time ago, actually. Archimedes, Euclid, all these great Greek mathematicians, for example, and others also did it this way. So that's a very important approach. Okay, so what do we get? So approximate arc length then is equal to a sum of these lengths. So let's have some notation for these pieces. So for example, this would be A plus, so it would be a length of R of A plus 1 over n minus R of A, right? And then plus, so basically I just write it like this, plus length of R of A plus 2 over n minus R of A plus 1 over n plus a norm of R of A plus 3 over n minus R of A plus 2 over n. Okay, plus the last piece, of course, this piece is going to be, okay, so I already made a mistake here. I should have put here b minus a divided by. So let's, instead of this, I put b minus a over n, sorry. And then here 2 times b minus a over n, here b minus a over n. So I assume that b minus a is 1, but it need not be, so that's okay. Just add this extra factor of b minus a here and then put b minus a over. Okay. So we just, instead of, so because this point's coordinate is, so length of its, so let me put it like this, a plus n minus 1 over n times b minus a. Actually, this is, sorry, r of b minus r of a plus n minus 1 over n times b minus a. So the so again, I just refer you to this picture. This is a, b. This divided into n equal pieces, and each piece has length what? B minus a over n, right? Because we divide this and divide by n, so this is b minus a over n. So then coordinate of this point is a plus b minus a over n. Coordinate of this point is a plus twice b minus a over n, right? And then so. Okay. So once you do it this way, we notice that we can approximate each of these pieces by the derivative, because that's the difference, right? So we can now approximate these pieces by the derivative. So let's write. So this is approximated by norm of, say, r prime at, say, a plus norm of r prime at a plus b minus a over n plus norm of r prime times a plus 2 times b minus a over n. And then finally, norm of r prime at a plus n minus 1 over n times b minus a. Okay, so now you notice what we did. So we just have this curve. This is r of a. So these are these points. And so this is the derivative of the function at this point. So this is this vector. This one is the derivative at the next point, which is this vector. I mean, this is length of the vector, but to start with, we have a vector, right? And so on. And so you have 2 choices, right? You can either use these left points or right points, or you have many choices actually. You can choose also middle points. It doesn't matter eventually. What does this remind you of? This sum.
A Riemann sum?
It's a Riemann sum. Yes, exactly. It's a great Professor Riemann's sum. So this is a Riemann sum. One of the most revered mathematicians in all history is Bernard Riemann. So I have to write his name with like big R and stuff. So this is Riemann sum. So in calculus, you know, you remember how to calculate Riemann sums, how to calculate the limits of Riemann sums. In the limit, this Riemann sum converges to an integral, right? So assuming, e.g., r prime of t is continuous as a function of t. Remember, I'm saying r prime of t. I'm not saying r. R already, I used the continuity. I'm using actually differentiability of r. So I'm using that r prime of t is continuous as a function of t. There is one piece that's missing, namely we should also multiply this by delta t. Sorry. Because the derivative, we can just, what I'm using is this approximation. F of, for example, so let me write it in terms of R. R of A plus, B minus A over N minus R of A. I'm using the approximation of R prime of A times B minus A over N. We can always approximate it. So this delta T is, of course, B minus A over N. It's just the length of each subinterval. Okay, so we are almost there. So assuming that R prime of T is a continuous function of T, and then the above Riemann sum, the Riemann sum converges to an integral. Okay, so this integral is what we are all really interested in. So the integral is this. Integral from A to B norm of R prime of T. So this is what turns out actually to be our candidate, in fact, our definition of arc length. That's what turns out to be the right answer. So let me then write it here. Any question about the derivation of this? You're not responsible for the derivation, but it's good to understand why this concept was arrived at and how this concept was arrived at. It's important to understand the logic behind the concept. So let me erase, any questions there? No. Okay, so let me erase this kind of initial step and then I write it as a formal definition, so that's kind of very valuable, important definition. So, that definition is already there, formula, so let me but formally write it. So the length of the curve R of T T between B, A is given by L, I just write L as integral A to B norm of R prime of T. Okay. Of course, remember this was under the condition that R prime of T, for example, is continuous, for example. So I just put it, assuming R prime of T is, some curves, if R prime of T is not continuous, some curve may not have length even. It may be a continuous curve, but may not have length. Its length might be infinite even, or may not even exist. So there is some technicality involved. This kind of it says that the concept works well if your function is smooth enough, is differentiable enough. In one times differentiability is enough, or primitively continuous. You can lower this a little bit, relax this condition just a bit, but not too much. So, but for us, this is good. Any questions? So then we have this notion of arc length. So let's do an example, which is kind of maybe useful to do. So here's an example. Find the arc length of the curve R of t equal to 1 cosine of t sine of t t between pi over 2 and 0. First of all, let's see what kind of curve is this. I mean, this is not part of the answer that you're supposed to give, but it's good to know what kind of curve is this.
It's a spiral again.
This one?
Yeah.
Okay, that's an answer. That's good. Well, I mean, how do you guess I'm dismissive or anything? No, I'm not. Maybe home. Do you have an answer? Oh, there are some answers, it seems. Sorry. What does the R sum converge to? Oh, yeah. Okay. So there is a question. Right. The Riemann sum converges to this integral. And that's why we are defining the length as the Riemann sum. Did you get the answer? Okay, so I got an answer to my question, but there was a question by Lindsay. Did you get my answer, Lindsay? Okay, very good. So oh, okay, yeah. So there are two answers. So any other? So what kind of curve is this? It's a circle, but can you tell me a little more about this circle? Where it's located?
It's like on the x-axis it's 1, and then it's like that.
Yeah, it's really like, so I mean, this is extra that we're doing, but that's okay. X is always 1, right? So what does it mean? It means that X, O, Y, Z. So this is so X equal to 1 is a plane, right? It's a plane. This whole thing is the plane X equal to 1. And certainly my curve has to be on that plane because the first coordinate is always 1. But now when you look at the second coordinate, which is Y, and this one is Z, okay, so this is Y, this is Z, it's cosine t sine t. Of course, that's part of the circle, right? That's a circle. So if you go to this plane and look at this cosine t sine t, if t is equal to 0, where the curve starts at, for example, where this curve starts at? Starts at, well, if t is equal to 0, you have 1, right? And 0. So the curve starts at here. And as you move up in t direction, the y magnitude goes down and the z magnitude goes up, right? So this goes like this. So this is the plane, right? X equal to 1, this whole thing. And this is, in that plane, I draw some line parallel to this y-axis, some line parallel, so it goes like, and this is 90. So this is quarter of a circle. Quarter of a circle. Oh, now I noticed there was a mistake in one of the answers. Oh. Yeah, okay. The mistake is still is there. I'm glad that it still is there. R prime t, the magnitude of, so the question is, so the answer was the magnitude of R prime of t is always equal to root 5. Is that correct? What is the magnitude of, so, well, let's compute the t, and then we'll see. Well, maybe I misunderstood the answer, but I think I understood it. So, okay, so let's do this then. Here is, all right, so now what is length is equal to integral 0 to pi over 2 square root of x prime t squared plus y prime t squared plus z prime t squared dt. Look, I mean, this is nothing but, of course, norm of r prime t, right? Because it has three components, xt, yt, zt, and we just differentiate and we get that formula, right? So that's equal to integral 0 to pi over 2 square root of, so we have to take derivative of these guys. Well, what is x prime of t now? 0. Is 0, right? X prime of t is equal to 1 prime is 0. What is y prime of t? Well, that's cosine minus sine t squared. So that's sine t squared. I mean, so, sorry, this is negative sine t, sorry. And z prime of t is cosine t. Okay, so you sub in, you get 0 plus sine squared t plus cosine squared t. Okay, this is conveniently 1. All right, so this comes out to be equal to 0 to pi over 2 dt. What is this integral? Pi over 2. It's pi over 2. And does your answer make sense? Does it confirm your common sense, also your other knowledge? Yeah, because it's a quarter of the circle, but circle has radius 1, right? The circle has radius 1. This 1 has just shifted the circle, hasn't changed the nature of the circle. This is a circle that's just shifted along this line, along the axis x, the x-axis. Sorry, yes, it's just here. Otherwise, it's a circle here. And we are just computing the quarter of this. Okay, I mean, from my vantage point, quarter of a circle is this. You may see quarter of a circle in different ways. But it depends on the angle of view, right? Okay, so what was the problem that was referring to the earlier? Oh yeah, sorry about that. Yes, very good. So yes, that's correct. Center at 0, 0, 1. No, the center at 1, 0, 0. Yeah, that's correct. Yeah. Okay, very good. Thank you for all your answers and comments. And very good. Any other questions or comments about arc length? Okay, so now we are going to use some ideas that I said you may wonder why this is useful. Now we're going to put it to use actually. So let me erase this. So this is called arc length parameterization. So arc length. I'm still not totally convinced these are two words. Are you sure it's two
That's what
words?
Google said. I thought it was one word too.
Arc length. I can imagine this would be one word is also okay. What's that?
I was just saying, you can always say that you mentored it.
Correct. Arc parameterization of the curve. So, so imagine we have a curve R from some interval AB to R3. This is a given curve. So let's define a function. So let L integral A to B norm of R prime T, T, the length of this curve that we just computed, right? Length. So define a function S from interval AB to interval 0L by the following formula. S of T is equal to integral from A to T norm of R prime of tau d tau. First of all, do you know why I put tau here and not T? Yes.
T is in your parameters. Or
Is it?
I forget what those are called.
Limit.
Limit, thank you.
Is the upper limit of the integral. Exactly.
Dummy variable.
Exactly. Right. So T is not a dummy variable. T is actually the variable of this function. It cannot be get rid of. T is there. So I cannot use for the variable of integration for my dummy variable T. I have to use another thing. You could use anything you want except T. And of course you don't use S. Okay, so what is this function? This function just from interval AB just measures the arc length, right? So this is a function which works like this. So I mean, if you move up to up to point R of T, and here is R of A, right? So this function is S of T. S of T is equal to length of this piece of the curve, right? Length of this piece. That's good. So let us differentiate this. Let's compute the SDT. Because I made it as a function of T, so T changes, the length changes. Of course, as you move on. So can you tell me if this function increasing or decreasing, or could be increasing, decreasing, whatever? Can you tell me something about the nature of this function? In terms of increasing or decreasingness.
I assume it increases with increasing T.
Sorry?
It would increase as T, like as you move on. Increasing T.
Yeah, increasing T, yeah, with respect to T. Is it increasing? Yeah, so it's increasing. Why?
Because arc length is always positive. So as you're like measuring a longer distance on R.
Yeah, arc length is always positive, exactly. And as you move on, you are measuring longer and longer pieces of the curve, larger and larger pieces of the curve. So it stands to reason to believe that this is actually increasing with T. Now, there may be some cases where this function actually is kind of lazy, it stops in some intervals. It's like you're going from here to Toronto. You want to take some rest in some station in between, right? You stop there for 20 minutes. Of course, you are not increasing the, the distance that you're moving. So in that case, the thing is flat, it stops, and then you start moving. So the function at least is non-decreasing, but anyhow, so what is the STT now? Can you tell me what is the STT? What is the derivative of distance with respect to time? Yes?
The norm of R prime T.
What's that?
The norm of R prime T.
Exactly. This is norm of R prime of T, not tau now, right? It's T, of course, yeah. Because it's here T, so. So this means that the rate of change of length with respect to this parameter is given by a speed. Of course, remember this is a speed. Okay. So now what we are going to do, we can just write this function as a function of s, not as a function of t. So then what we do, change the parameter. So can now reparameterize r of t as a function of a new variable s, which is in this interval 0L, which is, of course, secretly we know what is the geometric meaning of this variable is. It's arc length. It's length. Okay, so then you get a function. I call it R of S. So what is R of S? Maybe, I don't know if, yeah, I think I still call it R of S. So what is R of S? So R of S should be indeed R of, so, well, I'm not sure if I should use R or maybe capital R. It doesn't matter. I think your book uses, I'm not sure what. But that's okay. So let me give you the concept. This is equal to R of T. So let me, no, I'll use capital R, sorry. So this is this one where S is equal to S of T. So this is our formula. So if you think about it, this is a bit subtle actually, because what we are doing, the function originally was a function of t. Now I'm writing it as a function of s. So I get a new function. I call it capital R, it's not little r. But capital R of s is little r of t, where s and t are related by this formula. So what does geometrically this mean? It means that I am really just parameterizing the curve in terms of arc length. So basically what it means, this is this one, right? So this is the function R going to R3. So here we go to this interval AB by this inverse function, right? So this function S, so this is S inverse. And then you have this R here. I mean, I won't ask you to reproduce this function in exam or anything. So, but this is a good way to think about what we're doing here. We are writing this function as a function of S, not as a function of T. So this function S is a function of t. So t is inverse function. So this is the inverse function. So these are all those concepts in calculus 1000 that you never paid attention and you were never asked to pay attention to, because the idea of inverse function, one-to-one, onto this sort of concepts. But here, they're kind of more important, a little more. Anyway, so this is called arc length reparametrization. And let me tell you, so we are finishing in 1 minute, let me tell you the main property of this arc length reparametrization. So reparametrization. So what we did, we have this function R of t. We got capital R of S. And remember, we had this S of t was this Z, so sorry, A to t, norm of R prime of tau d tau. And if you take derivative of this guy with respect to t, did I use capital S all the way? Yes, I did not screw this. So yeah, that's good. ds dt is equal to norm of t. So these rules, we're going to use soon. Now, can you tell me what is dr ds? Oh, no, capital S. What is the differential of r with respect to s? Yes.
Should it be like dt or dr over dt?
Yes, exactly. So we start from there. We just write dr dt. Then we use chain rule dt ds, right? dt ds. Right? So now I'm going to assume that this is the function. This r is essentially little r. Change anything. So what is this guy? The r dt. What is the r dt? Well, the r dt is really is what we found here. I mean,
Velocity.
yeah, exactly. This is the velocity, exactly. So this is velocity vector. Velocity vector. And what is dTds? What is this dTds? We are going to be done in a second. What is dTds? It's the inverse of ds dt because of, again, chain rule and all that, right? So this then, as a result, I can write it as dr dt times 1 over ds dt. dr dt times 1 over, now ds dt we computed is norm of r prime of t. And if you allow me to, instead of using capital R, if I use little r, then this would be really r prime of t, right? So this vector has unit length. So it's a unit length. So the lesson is that final thing, when you reparameterize in terms of arc length, you get a reparameterization that has unit speed. So as you traverse the curve according to its length, the change is with the unit speed. So this may make sense or may not make sense. I mean, you have to do a couple of problems about this to feel comfortable. And the reason I emphasize is that we're going to use this heavily in the next section, which is about curvature. So that it's one very, very important idea, curvature. So guys, sorry this went too long, 5 minutes. Yes?
Just before the end of class, I remember you said that you were going to talk about couple office hours that a TA is
Yes,
doing in person.
right. I will send you all emails through OWL, of course, about tutorials starting from next week. So that's good news, yeah. Yeah, this is unit tangent vector, exactly. Exactly. So let me now stop and then